Okay, this is lecture number 8, and we are talking about the velocity analysis of linkages. Now, this is extension to the previous topic, which is position analysis of linkages. So with the position, if you remember, we always had a linkage with, like sort of, we had, for example, we had a linkage with a given parameter with like the degree of freedom of the linkage, and we are required to conduct a position analysis. And the position analysis meant finding, if we look at the number or number our links here. So the position analysis means finding the angle of each link, if you like, the direction uh, of each link. Like in this case, I will have theta 3, and in this one theta 4. And if I had a slider, I'd also be trying to find the position of the slider on the link on which sliding occurs. So another, for example, if I have a linkage such as this one here, right, then my position analysis will be, and this will be theta 2, link number 2. The slider is link number 3, and this is link number 4. So each link has the information for each link. Like for link number 4, the information needed for the location is theta 4. For the slider, what I need to calculate is the distance R3, which goes to the slider. So the unknowns here, or what I try to find, unknowns are given theta 2. I try to find theta 4 as some function of theta 2, and R3 as some function of theta 2, so function 1, function 2. So this what I try to find here. So the position of each link, including the slider. If the link was a rotating link, the position means the angle of the link. If it was sliding, will be the sliding distance on which on the link on which the sliding occurs. Like in this case here, in this other case, my my given would be theta 2, and my unknowns are, or what I'd be trying to find would be like theta 3 as a function of theta 2. So possibly I'll just write it like that. I'll say here as some function 1 of theta 2, and then theta 4 as another function of theta 2 as well. So those would be in my position analysis. I have given, and then I have unknowns I want to find as function of the given value or the given parameter type thing, right? Now, the velocity analysis, so this is in the relation to position analysis, right? So this was in relation to position analysis. In relation to the velocity analysis, what I'm trying to find is actually the derivatives of these unknowns exactly. So I'm trying to find for velocity analysis, I'll try to find the derivative of theta 3, which is omega 3. I try to find the derivative of theta 4, which is omega 4. I try to find the derivative here, omega 4, and the derivative of R3, right? So this R3 here, the derivative of that is, we refer to this derivative as a sliding velocity. So in terms of velocity analysis, my given would be exactly theta 2 and omega 2, right? So I'm given the derivative of that, and my unknowns are would be omega 3 for this link here. For this linkage, my unknown would be theta 4, and this is theta 3. So this is omega 3, and this one is omega 4, and given omega 2. So it would be omega 3, and this will be some function of theta 2, and omega 2 is constant, usually will pop outside as a constant, right? And omega 4, which is another function of theta 2, and omega 2 as well, if it's constant, will be multiplied outside. Now I want you to realize here, I said function of theta 2 and omega, and theta 2 and omega 2, meaning that the angular velocity is not constant. It will depend on where theta 2 is. In other words, it will depend on the specific configuration, if you like, of the linkage, right? So the specific position of the linkage, if you like, right? So omega is derivative of the angle in general, right? And that's, if you like, units of that is radians per second. They call this angular velocity, right? So that's the angular velocity. All right. In the other linkage, my unknowns would be, so this other linkage here, this is R2, and this will be this link number 3, and so this will be R3. This here angle is theta 4 because this is link number 4, and this is theta 2. Rotates, link 2 rotates at omega 2. My given would be again omega 2, right? And then possibly I should get omega 2 and theta 2, of course. So given would be omega 2 and theta 2, and my unknowns would be omega 4, which is some function of theta 2 and omega 2, and well, I'll write this as d r3 dt, right? We're going to refer to this as v with a little s on top here, like just to say it's a sliding velocity, which will be another function of, in terms of the input link parameters, like the position and the angle. Vs here, I'm going just to say, to call this sliding velocity, velocity of sliding, or sliding velocity if you like. So this is sliding velocity. So, and it tells me how sliding of the slider, like how fast the slider slides on link number 4. So it's not the absolute position of link number 3. This is not the absolute position of link number 3 and absolute velocity, I mean. It's rather the sliding velocity on link number 3. Like I just, in this case, we'll talk about the things later on, but for the time being, just note that link number 3 over here has two velocities, one being on link number 4, the slider. So link number 3 is here. So this is link 3. It slides on link number 4 with this sliding, but also rotates with link number 4. So the velocity of link number 3 combines both velocities. In fact, it rotates with 4, but it has its own Vs. Then the velocity of this link will combine both, as we'll see later on, as we'll do the analysis. Now, so this is just the idea of this velocity analysis, what we are trying to find more or less. But how to find the information we're after, right? We can simply, for simple linkages, we can just differentiate the expressions we have obtained from the position analysis. So we can use for velocity analysis, right? Velocity analysis, we can either use calculus, right? We can use calculus by differentiating the position equations, and this will be for simple linkages where the equations are, if you like, are differentiable. Because I mean sometimes you get a situation where you don't have like simple equations relating to like a position of something to theta 2, but rather you have a number of equations together with sine and cosine and like more than like a procedure than an equation. It will be difficult to use calculus in this case, and this is where you get to use the other method, which is really the more appropriate, if you like, or the more relevant to kinematics, which when we use the kinematic relationships sort of thing. So this is the vector based on vector. This is the vector method. In this case, we are going to differentiate, right? By differentiating our differentiating our loop, right? Loop closure equation. Closure equation. So we differentiate our loop closure equation. Over here on the other side here, we sort of differentiate the position information we had obtained from our whatever, like from trig or from the vector method, right? Okay, now let me say that, let me give you an example for using calculus. Like, let's start by the calculus method and give you an example here. So let's say I have a simple linkage which is something like that. Okay, let's say I have a linkage which is something like that. So and this slider slides in here, and over here I have link number 2, and I have two sliding motions, if you like. This here is link number 3 and this is link number 4, right? So, and I have my theta 2 and this here is R2, right? So if I want to find, it's easy to find like simple expressions here by saying, like for example, if a position here of any point is okay, this point is fixed here to this slider, let's call it point. If this is A, I can call this point B, sort of thing. So that's fixed here. So I can say, okay, now I have an expression for xb, which is simply R2 cosine theta 2, right? So this is the position location of the slider. This determines for me location of link number 4, or position of 4, right? So this position of 4. And if I differentiate that, I should be able to get the velocity of the slider 4 as well. Or if I want that also, if I wanted the sliding velocity like in this direction or whatever, then I need this location here, this distance. I can call this distance R3, whereby R3 is equal R2 sine theta 2. Again, when I differentiate that, this the R3 dt should give me sliding velocity up and down, right? So this sliding in this direction, right? Sort of thing. So this is like 3 sliding, link 3 sliding on link 4, like that. So now if I want to differentiate, let's get xb. So to get the sliding velocity here, like vb, right? So there is some velocity vb. I don't know which direction we take, but let's differentiate here. So now vb, of course, is, so don't forget I'm using calculus at the moment. So it's really dxb dt, differentiate xb with respect to time. But however, you realize here, xb is not function of time, but it's rather a function of theta 2. Exactly like r3 is a function, another function of theta 2, correct? Okay, now in this case, what I'm going to do is differentiate xb with respect to the parameter in which it's function, multiply by the derivative of this parameter with respect to time. So like a chain type differentiation. All right. Okay. So now I get here to differentiate the position information with respect to theta 2, my degree of freedom type thing. So differentiate the position with respect to theta 2, and then differentiate theta 2 with respect to time. When you do that, what you get is omega 2. So this here is equal to omega 2. So this means straight away VB is omega 2 dxb d theta 2. So it's a simple expression. You differentiate that with respect to theta 2, you get minus cosine. So this is minus r2 omega 2 minus sine theta 2. So this gives you some idea on the sliding velocity. This is expression for the sliding velocity, and you can tell here it's negative because as omega 2 is positive, so for the velocity we are going to take for the angular velocity, if it was counterclockwise, so I'll take this as positive, right? So positive omega will be counterclockwise. So I'm going to put a note here saying positive for counterclockwise, right? And negative for clockwise. Okay. So now, why is it positive for counterclockwise? Because as you see in this example, as if the crank rotates counterclockwise, theta 2 is going to increase, right? So this means that the rate of a change of that is positive because the variable is increasing, right? Type thing. So this will apply, and I measure all my angles from the positive x direction as agreed before, and this will apply to all angular velocity. All right. So okay. So in this case here, as omega 2 is positive, I get a negative velocity from this expression for the range from like from 0, theta 2 equals 0 to pi, which makes sense to me because as the crank rotates all the way from the right hand side to the left hand side, it will be dragging the slider 4 to like in the left direction, right? Which like the opposite to the x axis type thing, and this is a negative velocity 100%. And then as theta 2 goes above pi, and then because now the crank is coming back in the other direction, then you get a positive value for the velocity because the VB is going um, because the slider 4 is going in the right direction. So that's a simple expression which I could for xv, which I could differentiate easily to get some velocity information. And also if I wanted, if you want to plot that, you can plot it easily because it's simple sine expression like theta 2 from 0 to pi or whatever, or to 2 pi. In the middle here, you have negative velocity, and then you have positive velocity, and the maximum value of this velocity is equal to r2 sine omega 2. That's a max, right? This is a max value of the velocity. So you can get information, and then you can tell that the slider 4 stops at when theta is equal to this here. So when theta 2 is equal to 0, VB is equal to 0. When theta 2 is equal to pi, VB is equal to 0 because the slider has stopped at the other end over here type thing. So this gives you the two stationary positions of the slider. And then this is how you get your you get the extreme positions or stationary positions mathematically by taking the velocity expression and equating this to 0 to find the stationary position. So get the stationary or 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 the extreme, right, positions of of 4, link number 4, by VB equals 0. That's this idea. Then also, if I wanted the slide information on the sliding velocity, when I say sliding velocity, I always mean a link that's sliding on another link, in a link other than the ground. Like I differentiate R3, which is this vertical distance here, R3, and then it's the expression R3 is R2 sine theta 2. So we'll multiply. So now I have R3 is R2 sine theta 2, just writing here for reference. Then if I wanted V sliding, it is dr3 dt, which is dr3 d theta 2 times d theta 2 over dt, which is omega 2. So it's really omega 2 dr3 d theta 2, which is equal to, oh sorry, that's omega 2. So that's r2 omega 2 cosine theta 2. This is the sliding velocity, right? That's sliding velocity. All right, and you can plot it also again at theta 2, and you can tell, you'll be able to tell when you plot it where the slider is going to stop momentarily on link number 4 type thing. All right, this sort of information. So over here, because that's a simple case, and I got simple position equations such as this one and the x equation, and then would be simple to differentiate those by using the rule. Normally the chain derivative type rule, or differentiate theta with respect to time and differentiate your expression with respect to theta type thing. And that's a common thing. Right now, if we look at another example, so let's take another example. So let's take example 2. Let's assume the other one. We'll call it example 1. Okay, no, I didn't just put one next to this here. And then this will be my example 2. A possibility, let's say you have something like that. So you have here a disk which is fixed off center. So that's fixed over here. So so it'd be like a crank, if you like. And then I have over here a cam, a flat faced follower. So this now becomes a circular cam rotating a flat faced follower, right? So this is circular cam, and this is, we call this flat faced follower. So this course does have a part we will talk about cams in more detail later on in the semester. Now I wanted to also, my unknown here will be the follower location y, and my known value would be the angle of the cam, right? Angle theta 2, if you like, and I can call this distance r2 if I want to, because I can too. This distance here, that's fixed, and what, like where the thing is touching, and this is R, and that's constant. Okay, so this will always be 90 degrees. So I can write an expression for y by saying, and I can go y is equal to R plus this vertical distance, which is R2 sine theta 2. That's why. Right? That's a simple expression for the like for the velocity, for the position analysis. So my known, like given, would be theta 2. My unknown is, as I said before, always look for the position of every link, and my link here of nodes is the cam, which is link number 3. So that is why, then that's a function of theta 2. And we got the function, it's simple. So I want the cam velocity. I can say, okay, cam, the forward velocity, cam velocity, normal will be constant, will be omega 2, which is d theta 2 dt. And then over here, this will be dy d theta 2 times d theta 2 dt, which is omega 2, right? Times dy d theta 2, and that's omega 2 r2 cosine theta 2. So it gives you the velocity of the follower. And you can tell from this equation, so it's like the follower does, it's like a cosine function. Again, it's theta 2, and you can plot it without a problem type thing. And be able to tell when this is big, right? So when the follower is going to stop at which position, which will be the stationary position or the extreme position of the follower. Obviously, when theta 2 is equal to either 90 or 270. In this case, when R2 is vertical upwards or downwards, then the follower will be at the extreme positions, and the difference between those two, the distance between the two positions will be like 2R2 or something. This will be the stroke of the follower type thing. They call this the lift, the follower lift in CAM notation. So, or the rise of the follower rise as well. Okay, so now this is equal to get extreme positions, and to find the extreme positions, as I said, if v equals 0, right, get stationary positions of follower and get rise, the follower rise, right? Okay, sort of thing. So you can tell that's a sine, and you can plot a cosine curve, no worries at all. If this was pi over 2, and right, sort of thing, and that's pi, and this is 270, 3 pi over 2, where thing will be equal to 0. So over here you get velocity, and so you get something like that, like this normal cosine curve or v type thing. So right, so you can do sketch those ones if you like. And then another interesting example, which is not very simple, but you can always differentiate because you get closed form equations. Example 3, if you remember, this is specific example here, which do call this R2, and this was R3, and this was the slider crank linkage, as we called it before. So now if you remember, this was theta 2, my angle theta 2, my angle theta 3 was here, and this was the distance x, if you like. You can call it xb if you like, no problem. And then remember the equations. I remember something like R2, like cosine was sine theta 3 was R2 over R3 sine theta 2 type thing, wasn't it? Something, or it was, did I have a negative sign in front of that? Let's check the equation we obtained before. And then also I had, based on this notation, possibly I should have a negative sign because because the angle here would be greater, theta 3 is greater actually than like it is in the fourth quadrant. And then cosine theta 3 was equal to square root 1 minus r2 over r3 squared sine squared theta 2. From memory, we had this expression before, and x was equal to r2 cosine theta 2 plus r3, multiply this by, just make some room here, so plus r3, multiply this by 1 minus r2 over r3 squared sine squared theta 2. We had those expressions. Then in this case, if I want to calculate um, the angle, the velocity omega 3, I can just maybe differentiate this expression here. So if we differentiate both sides of this expression, you get, when you differentiate that, so both sides I have functions. I have, when I differentiate this sine, so d sine theta 3 dt on the other side minus r2 over r3 d sine theta 2 dt. When I do my derivative, then when I differentiate that, I get from over here, this I'll get here, differentiate d sine theta 3 d theta 3 d theta 3 dt, that's equal to minus r2 over r3 d sine theta 2 d theta 2 times d theta 2 dt, which is omega 2. And from this expression, I can say, okay, so this sign here would give me cosine theta 3 times omega 3 being equal to minus r2 over r3 cosine theta 2 times omega 2. And then I have an expression for omega 3 minus r2 over r3, right? Cosine theta 3 underneath. And over here, I have cosine theta 2. And also, I have omega 2. So I'm just going to chuck omega 2 in here. Then cosine theta 2, and I put theta 3 underneath, cosine theta 3 underneath, which I got from here. I can now take this cosine theta 3 and plug it in my expression to have only theta 2 on this side of the equation. So theta 3 then will be equal to minus r2 omega 2, right? Cosine theta 2, divide this by r3 square root 1 minus r2 over r3 squared sine squared theta 2. All right, so this here gives me an expression of theta 2 as function of the angle theta of omega 2, omega 3 as a function of the angle theta 2, and the crank velocity omega 2. Now, I can straight away from this expression, I can tell that when this cosine term is equal to 0, then omega 3 is going to be equal to 0. And if I equate this to 0, so to find extreme positions, so I can say, if to find extreme positions or stationary positions, same thing, positions of what? Of link number 3, of link 3, because I'm now talking about omega 3, and if I say omega 3 is equal to 0, and this would say, okay, and what it will give me that omega 3 is equal to 0 at cosine theta 2 being equal to 0, i.e. theta 2 will be equal to pi over 2, 3 pi over 2, and this sort of it would repeat itself after that. So you can tell this means over here when the crank is vertical, so the crank is vertical like that, right? So that's theta 2. Over here, omega 3 is equal to 0. And the other one is when the crank is also vertical, right? This here, omega 3 is equal to 0. So this angle here is 270, right? So this, the crank here, R2, the crank R2. So now you can tell this is the maximum travel, if you like, for the conrod upwards and downwards will happen when theta 2 is equal to either 90 or 270, and you can tell from that, you can get more info from that. You can get the different angles, the angle theta 3 at this specific point in time, because you can go back to theta 3, calculate the expression from sine and cosine, and to plug those angles here and find what will the value of theta 3 will be equal to, type thing. All right. So now if I wanted also to differentiate my position, my slider position equation, and find the sliding velocity, I can also do that, because just sliding the expression again for x was r2 cosine theta 2 plus r3 1 minus r2 over r3 squared sine squared theta 2. And some people find this expression easy enough to differentiate, and then they can use calculus to do the velocity analysis of this linkage. And to differentiate it, you get the velocity, which is dx dt, which is again it's omega 2 dx d theta 2. So I need, at this point in time, I usually need to differentiate with respect to theta 2 multiplied by omega 2 to get the velocity of the slider. And then this derivative, if we, okay, let's find another color to do derivative, then v will be equal to omega 2, and let's differentiate inside. Cosine will give me a negative, so they will negative sine, r2 negative sine theta 2, and over here I have r3. I need to differentiate this term here, which is a square root. So the way I differentiate the square root is dividing 1 on the square root. So divide by that, r3 squared sine squared theta 2, and then at top you need to multiply here by the derivative of what's inside the square root. So this will give me minus, right, here r2 r3 squared 2 sine theta 2 cosine theta 2. So this is the derivative. If you want to simplify this a bit, you can by saying, okay, that's I can take outside here, so that's r3. I have this is r3 squared, and that's r3, so maybe one of them will cancel with that, and then uh, I will have r2 squared at this end, and then I'll be able to take r2 as a common factor from this expression as well. So, and this will leave me with over here with the ratio r2 over r3. So I can, if I want to simplify this further, I can take r2 as a common factor. I can get negative also as a common factor. So I can go r2 omega 2. Inside here, I have sine theta 2, right? And then this will give me a plus r2 over r3 at this end here, and I can either leave those multiplied together if I want to, that which is quite possible, or I can, if you wanted to have combined those together in assign to theta 2. It's quite possible as well. So you can combine those in sine 2 theta 2 if you want to. You can do it like that, or you can leave it if you like. That's not a problem. So if you decided to leave that, you can just go, all right, so that's sine theta 2 cosine theta 2 on the square root 1 minus r2 over r3 squared sine squared theta 2. And this will give me an expression for the velocity of the slider. And when I look at this, I want to be able to tell when the slider is going to stop or going to be stationary. I can simply just say when theta 2, because I can take theta 2 from that as a common factor. If you want to, you can take theta 2 as a common factor. So when theta 2 is equal to 0, when sine theta 2 is equal to 0, then the slider is going to be stationary, right? So when sine theta 2 is equal to 0, v is equal to 0, and this will happen. Theta 2 will be 0, pi, 2 pi, and all the thing repeats itself. And you can tell this is common sense, because when theta 2 is 0, this means the slider is at this maximum throw at this end here when theta 2 is 0, and then when theta 2, so here theta 2 is equal to 0, theta 2 here is equal to pi, and then the slider is here type thing, right? So the crank has rotated to the other end, and the distance is, if you like, the stroke, which is equal to 2r2. So this distance here is r2, this distance is r2, this distance is r3, and this distance here is r3, right? So you can get stationary positions again from the you can get stationary positions from the velocity equations. I'm just repeating what I said earlier. Now, the other method to do the velocity analysis where really the linkage don't lend themselves to easy equations like which you can differentiate is to use the vector methods. So by differentiating the vectors of the loop closure equation. So here, velocity analysis using vectors. I'm saying we're really differentiating the loop closure equation more than anything. So if you remember, the vector was our vector, like this is point A, right? That's point A. I'm just repeating quickly something I said before. So this here is a distance. I'm going to call this RA, for example. This is angle theta. I call it theta A or whatever you want to call it. And then let's say I want to differentiate that. So this here will be my vector RA. So RA is equal to RA and the angle theta type thing. So I want to differentiate that. You can, when you differentiate, you can look at the cases. The most general case is RA changes and theta changes, right? Okay, don't forget that theta changes like that. So this is omega, which is d theta dt, all right, sort of thing. But sometimes also RA can also change, but I'm going to do this later on. So RA can also change. For example, if I have a slider like that, right? So that's the slider, and this here is A. So and then sliding, there is a sliding velocity involved. So and this is theta. So it rotates, the link rotates on which sliding takes place, rotates at some velocity omega, and the slider slides on top of that, and my RA goes to the slider. So in this case, dra dt is the sliding velocity, and d theta dt is my omega. So I can take the case, the most general case, where, and I will, because I see these situations in my linkages where sliding occurs um, on like a link that rotates, simple to the example I gave you earlier, or something I drew earlier here, which was this linkage here. For example, like this linkage right here, the sliding occurs on a link that rotates, and in this case I will need to take into account the fact that the sliding takes place, because I need to calculate the sliding velocity. That's quite important, right? Okay, but I'm going to take first start with the case where sliding does not occur, like okay, cases for RA equal constant is a 4-bar chain. So the 4-bar chain is like that. That's an example. If you like an example, I should write really an example. An example is, so I have R1, that's constant, and R1 is constant. Here R2 doesn't change. R3, and the length R3 is constant. R2 here, the length R2 is constant, and this was R4, and my length R4 was constant. So in this case, R is constant. So when you differentiate, I don't take into account that R is going to change. So I take the case I'm going to explain right now, which with constant RA. So what happens with constant RA? With RA held constant, when you differentiate, so my RA is RA AJ theta, right? When you differentiate that, what do you get, right? You differentiate, if you differentiate d RA d theta, when RA is constant, you differentiate dj theta d theta. When you differentiate dj theta d theta, you only rotate this by 90 degrees. So the result is theta plus pi over 2. I'm going to prove this in a second. But this is what you do. It's as simple as rotating the angle by 90 degrees, or putting on top of a j, instead of just theta, theta plus pi over 2. This is the when you differentiate the a j term type thing, right? And let's prove that. We can prove it by saying a j theta is simply cosine theta plus j sine theta, correct? Okay, so when you differentiate that, dj theta d theta, cosine is minus sine plus j, that's constant, and then here I have cosine theta instead of sine theta, derivative of sine theta. Okay, and now minus sine theta is really cosine theta plus pi over 2, and cosine theta is only sine theta plus pi over 2. You see what I mean? So this is my cosine and this is my sine, and you can minus sine, and you can prove that. So because, for example, if you want to remember expansion of the cosine function, cosine A plus B is cosine cosine minus sine sine, right? So cosine theta, cosine 90 is 0, minus sine theta, sine 90, which is 1. So you get minus sine theta. And over here, when you expand the cosine function, the sine function, it's cosine theta, cosine 90, which is 0, plus cosine theta, sine 90, which is 1, and you get cosine. So they are equal. So in fact, when I differentiated d ej theta, d theta is something like that, which is this one plus pi over 2 gives me this one, is a derivative. Okay, so in fact, that's how we write it. So we write d e to j theta, d theta is equal e to j theta plus pi over 2. This is the concept of this derivative. Okay, so now if I differentiate this with respect to time, now if I go d ej theta dt, of course, again, I differentiate with respect to theta times d theta dt, which is omega, right? This term here is omega. So this gives me omega e d e j theta dt, which is omega e j theta d theta, sorry, plus pi over 2. So what you do, if you then differentiate the term e to j theta with respect to time, you add 90 to theta and you multiply the term by omega, which is d theta dt. Okay, so now my vector ra, which is ra e to j theta, if I want this to be velocity like va, right, which is d ra dt, is really, and I keep this constant, so it's really daj theta dt, which is will be ra times omega. Now systematically we do this now, j theta plus pi over 2. That's as simple as that. And we can take an example here. So one example can be the case where I have like a four-body chain can be a good example. So here I have this is point A and this is point B, and I have my length R2, R3, R4, R1, they are all fixed, and I have my angle because now I have to do my loop equation, so that's R2, and the angle from X axis to R2 is equal to theta 2, and this here is R3, and then the angle here will be equal to theta 3, and this one here is R4, and the angle here will be equal to theta 4. All right, so on the side, don't forget to introduce your vectors. So here I'll have R1, length R1, and E j theta, this is 0, really this angle is 0. So, and then R2 is R2 A j theta 2, right? And then R3 is equal to length R3 and direction theta 3, and R4 is equal to constant length R4 and direction theta 4, right, sort of thing. So now these are the vectors on the linkage, and I can just add them together to do my loop closure equation. And then the loop closure equation will be R2 plus R3. This is this side of the loop, and the other side of the loop will close with that, which will be R1 plus R4, and we can simply now just say, okay, right, we can replace this by the, if you like, we can replace those by the corresponding polar form. So here, this is the polar form here is that, and the polar form for R3 is theta 3, and that this will be equal to R1 AJ 0 plus R4 AJ theta 4. Okay, so now this is my equations in a polar form, my loop closure equation. So don't forget that's loop closure equation. Now, and with this equation previously, now I want you to pay attention to what I'm saying right now. We used the loop closure equation previously to calculate the angles theta 3 and theta 4 as functions of theta 2. So when we do velocity analysis, we take it from there, from this point on. So assume at this point in time that we have expressions for theta 3 and theta 4 as function of theta 2, and then we'll move on to do our velocity analysis, right? So I'm not going to repeat the velocity analysis again. We'll use those values, theta 3 and theta 4, in the velocity equations, and the hope is we'll have them produced previously and we can work out the values of these angles, right? So now at this point in time, now I have my loop closure equation in a polar form, and I simply just differentiate that. So when I differentiate my equations, I differentiate every term separately. So now I'm going to differentiate this term here, and you can tell this will give me now systematically R is constant. So I'll add 90 to theta and just multiply by omega as I could prove this here, right? Right. So now I do that. So when I do the derivative, this will be R2 omega 2 multiplied by omega, and you add 90 to your angle, or pi over 2, right? Okay, that's plus R3 omega 3, which is the derivative of the angle concerned, like in this term, right? E j theta 3 plus pi over 2, that's equal to, when I differentiate this, both terms are constant, so I get 0, and I differentiate that, so that's a 0 vector if you like. Okay, that's a vector 0. When I differentiate this, I get R4 omega 4 a to j theta 4 plus pi over 2. Now I've done my differentiation. I obtained, this is the velocity equation now, which I'm going to manipulate to find the two velocities I want to find. So here my unknowns are omega 3 and omega 4, because I'm doing velocity analysis, right? Don't forget velocity analysis. So I want to find the velocity, as I said before, I take it as the angles have been found already. So now I do that. So next step, so now I differentiate every vector at a time. I want just you to note something here very important. There is the difference between I differentiated every vector, but differentiated R2. So this was R2, and this is a derivative of R2. When you differentiate R2, you get the velocity of point A, the real velocity of point, actual velocity or absolute velocity of point A, because R2 relates point A to the origin of the frame, which is like that. Let's call it O2, right? So because R2 is an absolute position vector. I did use this term before. When you differentiate an absolute position vector, you get an absolute velocity. But R3 is not that. It's a relative position vector. So when you differentiate R3, you get relative velocity. You get a relative velocity. So when the derivative of R3 gives you velocity of point B with respect to an observer standing or attached here to point A. So it does not give you the real absolute velocity of B, right? Maybe the velocity of B, you get it when you differentiate R4, because it relates B to a stationary point, right? So if you differentiate R4, you get an absolute velocity for point B. But you differentiate R3, you get a relative velocity, because R3 is only a relative position vector. This is very important. So this here is a relative velocity term, right? And this one here is absolute velocity term, and the other one is absolute velocity term, because it gives me derivative. This is the velocity of B, if you like, this one here, with respect to the stationary point. All right, so in any case, now we'll move on. That's more like a concept than anything I want you to be aware of. So I want you now to, yeah, we'll go ahead and now try to find a mathematical expression for my velocity. So what the way I'm going to do that is by like expanding my terms or into real and imaginary type thing. So I'm going to say real is equal to real. Real on one side is real on the other side. So when I go real, I have R2, right? Omega 2 cosine theta 2 plus pi over 2. That's real, correct? When you say cosine theta plus pi over 2, like this specific term, theta, cosine theta plus pi over 2 is equal to negative sine. So this will be minus R2 omega 2 sine theta 2. So when I say real, for the real, I'll get negative sign for each angle. Even though real means cosine the angle on top of E, right? But because I have 90 degrees added to the angle, then this cosine will become minus sine the angle itself. Okay, that's one thing I want you to be aware of. When I say imaginary and get now R2 omega 2 and then imaginary is the sine term. So sine theta 2 plus pi over 2. And then when you say sine, so that's R2 omega 2. When you expand the sine, will give you sine cosine, which is cosine 90 is 0 plus cosine theta sine 90 which is 1. So we'll give you cosine theta 2. All right. So the imaginary will have cosine appearing. It should be sine, but was sine theta plus sine theta plus 90, right? So it became cosine theta when I simplify. So I want you to pay attention to that because we are going to do this a fair bit without explaining every time I do it. So when I go now, real is equal to real. Real on left hand side will be R2 omega 2, right, minus sine theta 2, right? Then minus R3 omega 3 sine theta 3 is equal to minus R4 omega 4 sine theta 4. And then uh, when I say imaginary is equal to imaginary, imaginary one side is equal to imaginary on the other side. And then imaginary will be like it's sine theta plus 90, which is cosine theta. So I'll have R2 omega 2 cosine theta 2 plus R3 omega 3 cosine theta 3. That's equal to, this will be equal to R4 omega 4 cosine theta 4. R4 omega 4 cosine theta 4. Now I have equation 1 and equation 2. We need to solve equation 1 and equation 2 to find, we need to solve 1 and 2 to find expressions for omega 3 and omega 4. All right, so I'll leave this till the next lecture. We'll start the next lecture by this one because we can just either solve using the elimination method we learned previously in high school, but then also we can be more insightful about it and end up with better forms and stuff like that. So I will leave it here, and my next lecture, lecture 9, we'll still be talking about position velocity analysis using vectors, and we'll continue. We'll try to complete this example in the next lecture. Okay, bye for now. Take care and try to solve as many examples as possible. And if you got stuck, please drop us a line on Moodle or by email. Good luck.